Hello and welcome to another one of these ADD videos. Today we're going to be discussing the concept of solving higher order differential equations using power series. Whenever we have a differential equation, and if you're asked to use a power series to solve it, what you're going to do is you're going to let y equal a power series. And the general form of this power series will be as such. We're going to have y equals the summation from n equals 0 to infinity of a sub n times x raised to the n. If this is your basic premise for y, then you can derive this using your power rule that you know from calculus. And when you derive this, what you're going to get is this. Y prime becomes, I want you to notice that the index was 0 and now is 1. When you plug in a 0, x to the 0 is 1, and you're going to get a constant. So the derivative of that constant becomes 0, so therefore the index has to go up to 1. There is no first term. It's gone. Then, for the power rule portion, you bring down the exponent, subtract 1, just like you did in calculus. Constant comes along for the ride. You can then take the second derivative, and the second derivative will look something like this. And again, we took another derivative, so the index is now 2. We have a sub n times n minus 1, all times x raised to the n minus 2. Now, all we did was just use the power rule one more time. N minus 1 comes down, gets multiplied as a coefficient, subtract 1 from the exponent, you get n minus 2. All right? So what are the steps? What must I do in order to solve a differential equation using these power series? Well, first thing, of course, is you're going to start out with letting y equal this. Find the derivative and the second derivative, if you need to, the third derivative, depending what your differential equation looks like. And then the steps are going to be as follows. You're going to plug in these derivatives and the y into your differential equation and simplify. You might have to multiply some x's. Remember, if you multiply like bases, you add their exponents. Once you plug these derivatives and the y into your differential equation and simplify, your next step should be to try to convert all of the exponents in just x to the k's, or some variable to the first power. Typically they use k. So if I have an n minus 2 up here, that needs to be a k. So what I'll do is I'll let k equal n minus 2 so that I can replace it and make it x to the k. Well, if I do that, then all these n's have to become k's. So what you do is, because you know what k equals, n minus 2 in this case, then you can add 2 on both sides and get that n equals k plus 2, and everywhere you see an n, you need to plug in a k plus 2. And what should happen is that the indices will change, as well as your n's, into variables of k, or whatever you choose. Okay, so again, you're going to let the exponent equal some variable to the first power, and then solve for n, and plug in what n equals in terms of that variable into each of these. So they should all be x to the k when you're done. Now when you do that, all the indices again will change, and your goal will then be, let's convert all the power series to the highest index. If I convert all the exponents and 1 is the highest index I find, all of the series need to have a starting point of 1 so that we can factor out a common series in the next step. So what we do is we plug in 0 here and here for n, or k if you substituted, and you'll get something like a sub naught times x to the 0 is just a naught, because x to the 0 is 1. And then you can pull it out of the series, the power series, as an a naught plus your power series, and now the index will go from 0 to 1. And they will match up with the other one that you have in your differential equation. So this will take a little bit of practice, as everything else, but you're going to be plugging in your values again into your power series to try to get the first few terms out so that you can match with the highest index that you have. All right. Again, it's crucial to first switch them to x to the k first, or the same variable to the first power. When you do that, the indices change. All right, so then at that point, you're going to factor out that common summation, x to the k, and what's left behind is going to be referred to as your recurrence relation. The recurrence relation, when we factor out the common summation of x to the k, will give you the coefficients of your expanded Taylor polynomial. Okay, so this is the handout from calculus, and this was finding Taylor polynomials. So when you find your recurrence relation, what it's going to give you is this fc, this f prime of c, the constants, the coefficients that are found in your Taylor polynomial. And what you're going to be doing is you're going to be expanding it out to get your power series, your general power series. You can see that this is in terms of x minus c and all that good stuff, but it's the same basic premise that you're going to end up with either something that looks like this or that. Okay, Maclaurin is just a Taylor polynomial centered at 0, so all those become 0. This is on the 24hourtutor.com under the calculus section for Taylor polynomial. What's left inside is the recurrence relation. Once you factor out the summation, and that'll give you your tool that allow you to find your coefficients for your expanded Taylor polynomial. In order to get those coefficients for the Taylor polynomials, you need to plug in the natural numbers to the recurrence relation you got, and that'll give them to you. Okay. All this will be more apparent once you check out the example video. Make sure that you understand what's going on. Once you get the first few terms, 5 or 6 terms, enough to see a general pattern for your power series, then that pattern for the general power series will be your solution to your equation. All right? So again, recap. This is your function based on this premise, this foundation. We take the derivative using power rules. Then you plug them into your differential equation, simplify. Then you convert them all into the same x to the first power variable, some k or b, whatever makes you happy. I use k. So x to the k to the first power. No added numbers, no subtracted numbers. And then you make sure the indices line up, and you do that by plugging in the first few terms and eliminating them, pulling them out. Then what's left is your recurrence relation. You set it equal to 0. You solve the recurrence relation for one of the subscripts, a sub k plus 1 raised to k, in terms of the other one, and the next. And then you get a relationship between that one and the next one. Again, it'll become more apparent once you see an example. Then you're going to plug in numbers into the recurrence relation, you get the coefficients for your expanded Taylor polynomial, and then at that point you can use that to find the general pattern, the general power series, which will be the solution to your differential equation. So it won't be a function in terms of t, it'll be an actual power series that will be the solution. All right, so I hope this has clarified things enough to at least try a few problems. You might need to watch at least the beginner example video to see what I'm talking about, because this is a little abstract and there are some big words in here that might frighten some people. But always try to enter things with an open mind and a positive attitude, and it'll take you a long way. Thanks for watching. Have a great day.